Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the problems that are related to the CPU organization. So, this is majorly related to the what are the instruction format, how to represent the bus architecture. So, the first problem statement is a bus organized CPU similar to figure 1. So here this is the resistor configuration that are connected with the bus. So here various general purpose resistors are connecting with the decoder and with multiplexers the ALU. So the bus organized CPU similar to figure 1 has 16 resistors. So the number of resistors are 16 resistors with 32 bits in each. So an ALU and a destination decoder. So all these are connected that are shown, the connections are shown in the diagram. Now how many multiplexers are there in the A bus and what is the size of each multiplexer? The second question is, how many selection inputs are required for MUX A and MUX B? How many inputs and outputs are there in the decoder? How many inputs and outputs are there in the ALU for data, including input and output carries? Formulate a control word for the system, assuming that ALU has 35 operations. So the solutions for this problem statement is, the first one is here 16 registers with 32 bits in each. So each bit has to be connected with the multiplexer. So how many multiplexers can be required and what are the size of the multiplexers? So here each resistor can operate on 16 bits. So 16 by 1 multiplexer is the size of the multiplexer. The multiplexer can receive 16 inputs and give only one output. And these resistors can be connected with 2 multiplexers. So all these are 16 bit resistors. So 32 multiplexers can be required. And what are the input for the, how many selection inputs are needed for MUX A and MUX B? To select these 16-bit resistors, 4 inputs, 2 power 4 is 16. So 4 inputs are required to select one of the 16 resistors. Next, the third question is, how many input and outputs are there in the decoder? So decoder is here 3 by 8 decoder. Why? Because here 8 resistors are there. So here the decoders are 4 to 16 decoder. So that the 4 inputs has to be taken and 16 output can be produced by the decoder. And what is the size of the data input line is 32 plus 32 and 1 for the selection of the decoder. So 32 plus 32 plus 1, 65 data input lines can be required. And for the data output line, 32 for carrying the data plus 1 line for the selection input of the multiplexer. So 33 data output lines can be required. And what is the format of the instruction? How to selection lines and what is the bit sizes for each selection can be, for operation 6 bits can be required. So here total 18 bits are used to address the memory. So 3 selection lines can be required. select A, select B and select D. And here for each selection line can has the 4 inputs. So 4 bits of each. So total 18 bits are required for this bus organization. Next problem statement is the bus system of figure 1 has the following propagation delay time. 30 nanoseconds for the signal to propagate through the multiplexers. So the signal propagation delay time can be for the multiplexers is 30 nanoseconds. 80 nanoseconds to perform the AND add operation in the ALU. 20 nanoseconds delay in the destination decoder. And 10 nanoseconds to clock the data into the destination register. So 30 nanoseconds for the propagation delay of the multiplexer, 80 nanoseconds for add operation, 20 nanoseconds for destination decoder, 10 nanoseconds for the clock. What is the minimum cycle time that can be used for the clock of this type of bus architecture? So here is the clock that has to be generated, and for the multiplexers, the propagation delay to perform the ALU operation and the delay, the clock delay, all can be given in the problem. Now we have to calculate the minimum cycle time that can be used for the clock. So here the propagation delay time in the multiplexers is the 30 nanoseconds. And to perform the actual operation of add ALU operation, 80 nanoseconds. And these operations can be accomplished with the clock signal. For the clock signal, it should be 10 nanoseconds. So the minimum cycle time that can be required without storing the result is 30 plus 80 plus 10, 120 nanoseconds. Next problem statement is specify the control word that must be applied to the processor of figure 1 to implement the following micro operations. So the micro operations are specified with register transfer language. So what is the bus structure control word that can be used in this architecture, in the CPU architecture? The first operation is to perform the addition operation between two registers and storing the sum in another register. The second operation is simply data transfer statement. Third operation is decrement operation. Fourth operation is shift left operation on the register. Next operation is input operation. So how the control word has to be selected? So here we are performing the add operation. The add operation can be the memory referenced instruction. So the control word format is 010, and to reference the register, the control word can be in the binary form. So here the registers that are applied for the add operation are R2 and R3. Those can be selected by select A, select B lines, and the destination has to be the R1, and the operational code can be the add. Next is simply data transfer statement. So we can apply the complement operation. So the complement of A can be moved to the same register. So here it can be the register reference. So here the value can be the control word opcode can be the 100, and on the no destination register. So on the R4 itself, it has to apply the complement operation. Next operation is decrement operation. Decrement operation can also be a register referenced instruction. And here the value of R5 can be decremented by 1 and it can be moved to the destination same register R5. Next operation is SHL. So shift left operation. So here left shifting can be done on the memory word. So here the control word starting with 001. Next is input output operation. The input output operation has to be transmitted with the control word 000, and the input that is taken from the buffer FGI can be restored to the register R7. Next problem statement. Determine the micro operations that will be executed in the processor of figure 1 when the following 14-bit control words are applied. So, what are the referenced instructions in the binary code? 3 types of instruction formats are available. Depending upon the opcode of the control word, the type of the instruction format can be determined, whether it is memory referenced instruction, register referenced instruction, or IO instruction. So here it is 001. The micro operation can be the subtraction operation, and it is a register referenced instruction. And here 000 means it is an input instruction. Next 010 means it is performing the XOR operation. 000 is also the input operation. 111 is simply the shifting operation, shift right operation. So the control word that are applicable to these specific micro operations of the RTL. Next problem statement is a computer has 30-bit instructions and 12-bit addresses. If there are 252 address instructions, how many one address instructions can be formulated? So the total number can be 250 with 2 address instructions. So how many one address instructions can be formulated? So here 32-bit instruction. So the length of instruction is 32-bit. But it is a 2 address instructions. So address 1 and address 2 can be provided. And each address can be of 12-bit addresses. So here in the 32-bit, 2 addresses of 12-bit each, they can occupy 24 bits. Total is of 32-bit. The remaining 8 bits are used to represent the opcode. So this is the instruction format. And here 8 operations has to be performed. So 2 power 8, 256 combination of operations can be performed. And here there are 250, if there are 252 addressable instructions. So here total combinations are 256, and that only 250 instructions, 2 address instructions are used. So 6 combinations can be used for one address. So 252 address instructions can be used. So total combinations are 256. So 250 are 2 address, only one address are the 6. So here 6 combinations can be used for one address. How this one address instruction format can be? The 12 bits can be used for the address. So maximum number of one address instructions are 6 into 2 power 12. 12 address bit lines can be used. So there can be 24,576 one address instructions is a maximum number of one address instructions with this CPU architecture. Next problem statement is the memory unit of a computer has 256 kilowords of 32 bits each. The computer has an instruction format with 4 fields. So the opcode field, a mode field to specify one of the 7 addressing modes, a register address field to specify of 60 processor registers and a memory address. So instruction format can have 4 fields. Specify the instruction format and the number of bits in each field if the instruction is in one memory word. So what is the instruction format? So here 256K is the address space of the memory. To represent kilo, 2 power 10 combinations are required. To represent 256, 2 power 8. So total 2 power 18 can be used as address space with the help of 18 address lines. So the address bit can be is of 18 bits length. And 256K words of 32 bits each. So here the length of the instruction format can be the 32 bits. In this, the addresses to reference those address space is 18 address lines. So 18 bits are used for address. Next, the registers are of. So a mode field specify 4 parts are there in the instruction format. 60 processor registers can be used. So here to address those registers, so 6 bits can be used and the mode of operation can be occupy 3 bits. So remaining are the 5 bits to specify the operation code. So here 18 bits, 3 bits and 16 to point the register field. So total 27 bits. So after that 5 bits are added in order to fill the 32 bits. So the instruction format can point the 4 fields. One is the operational code. The operational code can be of 5 bits length. And next the second part is a mode field to specify one of 7 addressing modes. So to specify 7 addressing modes, 2 power 3 locations can be available. So 3 bits has to be used for to represent the mode field. And to represent 60 registers with these register organization, 6 registers can be enough. So these total can be 27. The total length of the instruction format can be the 32 bits. 32 minus 27, 5 bits can be used to represent the opcode. And the total instruction format to represent the 4 field is like this. Next problem statement is mini computers in the 80s. Example, DEC PDP 11 computers had 18 address signals and of course the 18-bit address bus. Okay. So here answer the following questions. What was the address space of these computers? So 18 address lines are there. What is the address space of this computer? What may have been the largest possible memory of the computers in bytes if the memory location is 1 byte? How long should the program counter of these computers be? What would be the need to change in these computers if you would like to increase the address space 8 times? So here 18 address lines are there. 2 power 18 is the address space. So that is 2 power 8 into 2 power 10. 256K is the address space. What have been the largest possible memory of these computers in the bytes if the memory location is of 1 byte? So 256 KB is the maximum capacity of this memory. Why? Because 18 address lines are there. 2 power 18 is 256 KB. and 18 bytes because the program can anywhere in the memory. So how long should the program counter of this computer can be? So each can has to point to the 1 byte memory location. 18 bytes are required. The computer program can be stored anywhere in this memory address space. What would be needed to change in these computers if you would like to increase the address space 8 times? So here add 3 address signals to extend PC for 3 bits. So 2 power 3 is 8. So 8 times if you want to increase. So the instruction format has to be changed to accommodate 3 more bits. Next problem statement is, this is depending upon the stack organization. The stack is very useful in the computer organization to store the return address whenever a branching or interrupts are called. So here the stack pointer points to the top of the stack. Push and pop are the two operations that can be applied over the stack. So here the problem that is pertaining to stack organization. A stack is organized such that SP stack pointer always points at the next empty location on the stack. So SP points to the next empty location on the stack. This means that SP can be initialized to 4000 and the first item in the stack is stored in the location 4000. So list the micro operations for the push and pop operations. So here this is the stack organization. SP is pointing at the location of 4000. So here what is the data register data that has to be moved to the memory that is pointed by the stack pointer that is at 4000 location. And SP can be decremented by 1. Next, there is the push operation, that is to insert the data in the stack. To fetch data from the stack, the pop operation can be applied. So here in order to move to the SP to the 4000 location, stack pointer can be incremented first. Then the data that is pointed by stack pointer from the memory can be fetched and can be stored in the data register. Next, write a sequence of instruction that will compute the value of x is equal to a plus b into c plus d using 0 address instruction, 1 address instruction, 2 address instruction, 3 address instruction. So here in case of 0 address instruction, the number of arguments applied to specify micro operation can be null. Generally, the stack organization can be used for this purpose. In case of 1 address instruction, 1 argument can be specified in the micro operation. Generally, the accumulator CPU organization is used for 1 address instruction. 2 address and 3 address instructions are register based instructions. The general purpose registers can be used here to perform the micro operations. By using these instruction formats, evaluate the sequence of x is equal to a plus b into c plus d. So in case of 0 address instruction, how this can be evaluated? In case of 0 address instruction, the stack organization can be used. So the expression can be first converted into postfixed notation. That is, the operands later on the operator can be specified. So here a plus b means the operands are ab. Next the operator is plus operation. Next c plus d means the operators are cd. Next plus is the operator. And between these two operands, multiplication is the operand. So here this can be first represented in postfixed notation in case of 0 address instruction. So here first the operands or arguments can be pushed to the stack. So push A, push B. So those can be, these two operators can be used for operand applicant. So here add is the operation. So A plus B can be performed here. Next push C, push D, and the add operation can be performed. Next, on both the top, we have to perform the multiplication operation, and the result can be popped to the X variable. So this is the zero address instruction sequence. Next is the one address instruction sequence. Generally, the accumulator based CPU organization can be used for one address instruction. Here, one operand can be stored in the memory and other can be used the accumulator register. So here, load A. First, the A operator can be loaded to the accumulator. Add B. Accumulator value can be added with the memory pointed by the B location. Store T. So A plus B can be stored in the T location. Next, load C, add D. Similarly, A plus D, C plus D can be performed, and this value can be multiplied with T, so that A plus B multiplication of C plus D can be performed, and the result can be stored at X location. So in this way, this is the sequence of evaluation of expression A plus B into C plus D, X is equal to in the one address instructions. Next is two address instruction use the registers. So here the opcode and the registers can be used to perform, to hold the operands. So here for storing A value in the first moving to the R1, B value to the R1, B value with which has to perform the add operation, B along with the R1, where R1 holds the A value, so that A plus B can be performed. Next, move C to the R2 and perform add operation, so that C plus D can be performed and the result is stored in the R2. And multiplication of R1 and R2. R1 holds the A plus B operation, R2 holds the C plus D operation result. Both can be multiplied and the result is moved to the, is stored in the R1 and is moved to the X. So this is the sequence of evaluation into address instructions. Here there is no need to specify destination register separately in case of two address instructions, but this is more simplified in the three address instructions. So in case of three address instruction, the destination register can be specified, source two source address registers can be specified. So here the A, B has to be added and the result is stored in the R1. Next, C, D can be added and the result is stored in R2. So X comma multiplication of R1 and R2 and the result is stored in the X. So this is the sequence of execution of micro operation in case of three address instructions. Next problem statement is, write a sequence of instructions that will compute the value of y is equal to x square plus 2x plus 3 for a given x using 3 address instruction, 2 address instruction, 1 address instruction. So the top two are the register referenced instructions. 1 address instruction uses the accumulator CPU organization. So in case of 3 address instruction, x square to evaluate multiplication x and x square and the result is stored in the z. So this is exactly equivalent to z equal to x square. Next, multiply 2 into x, that result can be stored in the y. Y is equal to 2x. Add y, z and result is stored in the y. So y is equal to x square plus 2x. Next, add y comma 3. For these 3 can be added and stored in the y. So this is the 3 address instruction sequence of the given expression. Next, for the two address sequence, the destination register cannot be specified. So, first moving the x value to the z and multiplication of this for the z to obtain the s square value. Next, move y value to the 3 and add z to the y. X square plus 3 can be performed. Next, move x to the z, multiply to z. So, to perform the 2x, these two can be used for 2x operation. This is for 3. Add these so that you can evaluate the x square plus 2x plus 3 expression using two address instruction sequence. Next, one address instruction sequence, move x, multiply. So, in order to get the x square and store it in the z, move x, multiply to 2x. Next, add z, add 3 and store the result in the y. This is the one address sequence of the given expression. Next problem statement is, consider a processor with 64 registers and an instruction set size of 12. 12 is the instruction set size. Each instruction has 5 distinct fields, namely opcode is the first field, next 2 source registers, second field, 1 destination register identifier and a 12-bit immediate value. So each instruction must be stored in memory in a byte-aligned fashion. If a program has 100 instructions, the amount of memory consumed by the program text is, and options given is 100, 200, 400 and 500. So the instruction consisting of opcode and operands. So the instruction size is 12 and 4 bits are required for opcode. Okay, so here 16 to address. So 2 power 4 is the 16. So 16 has to be 16 address lines can be needed. As there are total 64 register. So 6 bits are required for identifying a register. Next, 2 power 6 is 64. So as the instruction contains 3 registers, 2 are the source and 1 is the destination. So here 2 source register identifier, 1 destination register identifier. So 3 registers, 2 source registers, 1 destination registers, 3 into each register requires 60 bits, 18 bits are required for register identification. So 12 bits are required for immediate value as given. So total bits are 4 plus 18 plus 12, total 34. Okay. So here to represent the opcode and the registers, 3 registers, 18 bits and immediate value of 12 bits. So total 34 bits are required for the instruction format. The instructions are required to store in a byte-aligned fashion. So the nearest byte boundary after 34 is the 40. 5 bytes are. So byte-aligned fashion. So in order to get these 34 bits instruction format, the nearest is at 40 bits. So hence 100 instructions, the memory required is 5 into 100, 500 bytes, which is the option D is the answer. Next problem statement is, a processor has 40 distinct instructions, 24 is the general purpose registers, 32-bit instruction word has an opcode, 1 field is the opcode, 2 register operands and immediate operand. The number of bits available for the immediate operand field is. So as the processor has 40 instructions. So 2 power 6 is 64 and 2 power 5 is 32. But 40 instructions has to be addressable. So 6 can be considered, 6 bits can be considered for the opcode. As the processor has 24 register, number of bits for one register is 2 power 5. So it can be 32 registers. Next, total bits occupied by total 2 registers and opcode. The opcode is of 6 bits and the total 2 registers each of 5 bits each. So total 16 bits. So an instruction size given in 32 bits. Remaining bit field left are 32 minus this 16. 16 bits can be used for immediate value. Next problem statement is, a machine has a 32-bit architecture with one word long instruction. It has 64 registers, each of which is 32 bits long. 32-bit architecture, one word long instruction and 64 registers. It need to support 45 instructions. Number of instructions to support 45, which is have an immediate operand in addition to 2 register operands. Assuming that immediate operand is an unsigned integer, the maximum value of immediate operand is dash. So 32-bit architecture and each one word is equal to 32 bit. So instruction size, each instruction size is 32 bit. As the processor has 64 registers, so here 2 power 6, 64. So 6 bits are used to represent the registers. As the processor has 45 instruction, number of bits that are required for opcode is 2 power 6 is 64, 2 power 5 means 32, so which is less than the 45. So we have to take the 6 bits to represent this in the opcode. So total bits occupied by 2 registers. Number of registers here is 2 register operands. So total bits occupied by 2 registers and the opcode. So here 6 is for the opcode size. This is the opcode size 6 and each register is of 6. So 2 registers are there. So total 18 bits. The maximum size is 32. 18 is for representing opcode and 2 register identifiers. So 32 minus 18, 14 bits can be used for the immediate value representation. So maximum unsigned value using 14 bits is 2 power 14 minus 1, that is 16,383 is the maximum value that has to be represented. Next problem statement is, a processor has 16 integer registers R0 to R15. These are the integer registers. And 64 floating point registers F0 to F63. It uses a 2-byte instruction format. There are 4 categories of instructions: type 1, type 2, type 3 and type 4. Type 1 category consists of 4 instructions, each with 3 integer register operands. So here the type 1 is performing 3 integer type of register operands. Type 2 category consists of 8 instructions, each with 2 floating point register operand, 2FS. Type 3 consists of 14 instructions, each with 1 integer and 1 floating point, 1 integer and 1 floating point. Type 4 category consists of n instructions, each with a floating point register operand, 1 floating point register operand. What is the maximum value of n? That means what are the type 4 maximum number of instructions? As the machine has 2 bytes, so 16 bits instruction format can be used. So it can be encoded 2 power 16 combinations. As the processor has 16 integer registers, number of bits for one register is 4. 2 power 4 is 16. As the processor has 64 floating point registers. So, number of bits for one floating point register is 6. Next, for type 1 category having 4 instructions, each is having 3 integer register operands. So, 4 into 3. 4 is for each integer register. 4 into 3, 12 bits will consume 4 into 2 power 12. So, it has to follow the 2 power 40 encoding combinations. Type 1 can be addressing those encodings. What is the type 2 category having 8 instructions? 2 floating point register operands. Each floating point register operand occupies 6. So, 2 into 6, 12 bits. So, it can consume 8 instructions total. 8 into 2 power 12. So, 2 power 15 encodings, the type 2 has to be taken care. Next, type 3 category having 14 instructions. And 1 integer register, 1 floating point register. Integer can take 4 bit, 4 encodings. Floating point taking 6 encodings, 10 bits. So, these are of 14 instructions, 14 into 2 power 10. So, 14,336 encodings can be taken care by type 3. Type 4 category instructions, number of encoding left is 2 power 16 minus 2 power 14, 2 power 15 minus 14,336. Total can be 2 power 16. In the 3 categories encodings we identified, those can be minus. So, 2048 encodings. So, the type 4 category having n instructions, each having 1 floating point operand will consume n into 2 power 6, which is having the 2048 encodings. Okay. So, n value can be the 32. So, these are the problems that I have discussed relating the CPU organization and instruction format and stack organization. And the reference for this video is the Computer System Architecture, a textbook by Morris Mann. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.